to analyze the stability factor of this circuit, what we are doing, we are going to apply Kirchhoff's voltage law. I'm going to apply Kirchhoff's voltage law in this path. So I'm going to take this complete path in the base side and I'm going to apply Kirchhoff's voltage law. So you can see there are two voltages involved, VCC and VBE, and I told you VBE will always oppose VCC. The effective voltage is VCC minus VBE. So VCC minus VBE equal to the current through RC is IC plus IB. So IC plus IB into RC plus IB into RB plus IE into RE. But you know IE is going to be IB plus IEC. So I'm going to write IB plus IC into RE. So see here, first resistance IB plus IC into RC. This is the current flowing to the collector resistance RC. The next one you see IB into RB, the current flowing to the resistance RB. And through RE, IE is flowing, but you know IE is equal to IB plus IC. So it is IB plus IC into RE equal to VCC minus VBE. So as we are familiar with the KVL equation, you have to apply it. You are going to write two KVL equation, one including the base side, one including the collector side. So we have applied the KVL equation, which is going to completely surround the base side. So from this equation, I can rearrange. See, I'm not showing the mathematical simplification. Please, you do that, work out that at house, okay? So from this equation, I'm going to find what is IB equal to. So group all IB terms together, take all the unwanted terms to other side. So see, if you find what is IB, this will be the expression for IB. So IB is equal to VCC minus VB by RE plus RC plus RB minus RE plus RC by RE plus RC plus RB into IC. You know that when you differentiate IB with respect to IC, because we have to compute the stability factor S, which needs this differentiation factor, DIB by DIC. See, the first term is constant because VCC is constant, VB is constant, RE is constant, RC is constant, RB is constant. So this everything is constant. So differentiation of constant is going to be 0. And when I differentiate with respect to IC, only this constant term will come. So minus of RE plus RC by RE plus RC plus RB. This is going to be DIB by DIC. Okay, see, in all the biasing circuits, one common thing what you find is this expression DIB by DIC. We find that because the stability factor involves that. So the formula for stability factor is S is equal to 1 plus beta by 1 minus beta into this this differentiation term DIB by DIC. And what we have got here, minus of this term. So minus of minus will become plus. The 1 plus beta by 1 plus beta into this entire term will be coming here. So this is going to be the expression for stability factor in collector emitter feedback bias. So this from the expression we can see denominator is very large. When the denominator is very large, the value of S is reduced. So logically you can say, since the denominator is having a large multiplication of terms and all the resistance will be in kilo ohms, the stability factor will be relatively very good. So I can say that the stability factor of this collector emitter feedback bias is going to be very much good when you compare to the collector emitter feedback and emitter feedback circuits. When you compare the performance of the collector to base bias circuit separately and emitter feedback bias circuit separately, when you combine both, that is going to give you a very good result in the form of reduction in the stability factor. See, remember, whatever biasing circuit you design, ultimately it should ensure that the stability factor is reduced. There is no use having a very high stability factor for a biasing circuit. Very high stability factor means the variation of collector current is very high in that circuit, which is not required by S. So please understand, any biasing circuit, only one requirement you have, the value of S should be as small as possible. So any doubts you have in collector emitter feedback bias, please ask if you have any doubts in this type of feedback bias, collector emitter feedback bias. Are things clear to you? We don't have any problem given for this in the textbook, so I don't have the multi-sim simulation to show you the live result. So it's in this combined technique in the two different techniques. We are going to combine it, so we don't have a problem exclusively for this circuit in the textbook. So I didn't have the circuit to show you the simulation result in multi-sim software. But theory wise, I think this should be very clear to you. We are not applying the KVL at the collector side here because It is not required because I got the expression for IB directly by applying the KVL in the base side itself. So in this direction, if I'm going to apply KVL, I got the expression for IB. I need DIB by DIC. So I got the answer and I found out the value of stability factor. Yes. And from the expression, mathematically, we can say this circuit will have a stability factor very, very less compared to your collector emitter feedback bias in compared to that of individual collector feedback and emitter feedback biasing circuits. So that can be assured from this biasing circuit.